Hi, let's continue with more on the theory of curves. And this time we want to give more examples than we used to in the previous videos. There will be three successive videos which focus on the question of shortest curves between points in a metric space. And in this video, we will focus on the Euclidean and Riemannian setting, and in non-Euclidean settings, there will be more interesting phenomenon, and that we will cover in the follow-up video. Okay, recall that any subset of a metric space becomes a metric space by the distance that it inherits from the ambient space. So if you start with any subset of the Euclidean space, it comes with this distance x minus y norm. That is the one it inherits. But then we can also talk about a new distance called the intrinsic distance. And what it does is it looks at the shortest curve that goes from x to y within x. So of course, if you allow within Rn, this will be just the previous usual distance. This quantity does not have to be finite. For example, it is infinite if there is no path between x and y. For example, if x is a collection of finite points, and in that case, the set of curves connecting x to y is an empty set, and by convention, infimum of the empty set is infinity, which agrees here with the fact that it is just too difficult to go in finite length from x to y. The easiest examples are, for example, the circle in R2, right? So circle is your S1 and it is sitting in R2. The intrinsic distance between 2 points will be the shorter of the 2 arcs connecting them. So in this case, it will be the length of this thing, which equals the measure of this angle in radians. On the sphere, again, sphere sitting inside R3, similar phenomenon happens, and that has a lot of applications. That's where the name geodesic comes from, meaning the geo for the geology. So, of course, it was always important to find the shortest ways to go between points on the roughly spherical Earth. And that, of course, airlines were very much interested in, of course. But okay, yeah, so in this case, it turns out that the shortest curves connecting 2 points are those that are parts of the great circles, the largest circle sitting inside the sphere, and you pick the shorter of the curves, the arcs that connects them. And given any 2 points, there is a unique great circle that goes through it. Check the Wikipedia articles on these topics because they are usually nice with good pictures and whatnot. So you can go with any other favorite shape of yours, torus, I don't know, Kleinian bottle inside R4, things like that. But the important notion we introduced here is that of the intrinsic metric, and that will come up again later in our examples. If you are familiar with hyperbolic geometry or simply with Riemannian manifolds, a nice metric on the disk in R2, for example, is an example of a metric on subset of R2 that is different from the usual distance. In this distance, you define the distance between 2 points x and y to be the smallest, so this will be the infimum of integral from a to b of gamma prime norm dt, where infimum is over all piecewise C1 curves that go from x to y. But this would be the usual Euclidean distance, right? The difference is that this new norm is a scaled one. So I put this subscript g. So here what you do, that the norm will be scaled by the factor of 1 over 1 minus the base of this tangent vector. So if this is gamma prime of t, the tangent vector, its norm will be its usual norm, but divided by distance of gamma t to the origin to the power 2, 1 minus that quantity. And as you see, if gamma t is closer to 1, if you are closer to the boundary, then this becomes very large quantity. So curves that go near the boundary become really long because this becomes very big, and curves that remain close to the origin are the shorter of them. And it turns out as a result of this that if you pick, say, two not very special points within your disk, the shortest curves will look like this. So they kind of gravitate toward the origin and then back there, and that is a shorter curve than this one because more part of this curve is near the origins, where this is small quantity compared to the straight line. But anyway, that's an amazing space, and it's a lot of fun to play around with it. Again, the Wikipedia article will have a lot in that. In general, when you are given a Riemannian manifold, so that is a manifold together with an inner product on the tangent spaces of the manifold, all abstract, but of course, pictorially, we always draw this. So if this is the tangent space, the derivatives of curves stay in this affine space, and there is a dot product in this space. So V, W, G is a linear, is a real value that of course changes smoothly along the manifold. And if your manifold is not sitting inside a bigger Euclidean space, then the only natural metric distance that you have is to do a similar thing we did with the Poincare disk. So you'll look at the shortest length of curves that connect x to y. So if you are traveling along this curve from x to y, its derivative at every point, say at this point, is a vector, and you can dot product it with itself in this G metric. And yeah, this is a well-defined real number, so everything makes sense. And you look at the shortest that you can get. And that defines, you have to, of course, prove a distance on this space. And this is like, we're using metric here. Actually, that's one of my bullet points here, that the metric here has two meanings. G is often called the metric, the Riemannian metric on the manifold. And this D is the distance metric. It's what it makes it a metric space compared to what makes it a Riemannian manifold. So we have to be aware of these terminologies. Okay, now that we know how to equip manifolds with a distance function to turn them into a metric space, and also we know that any subset of a Euclidean space is comes with two distances, the inherited one and the intrinsic one. So we are at a good point to discuss geodesics. So to be precise, a geodesic is a curve such that its distance of its endpoints equals the length of that. Remember that we always had length bigger than the distance of its endpoints by definition of a variation or length of a curve by taking the 2-point partition. So this was always true, and when this happens, we call that curve a geodesic, a shortest curve. We say a metric space is geodesic if any 2 points in that space can be joined by a geodesic, by a shortest curve. And here the definition, it's important that the definition does not require it to be a unique one. So it's at least there is one shortest curve that connects them. So with this definition, Euclidean spaces become geodesics because, well, the straight line connects them. We will see a more general result. In this circle example, even with the intrinsic distance, it is geodesic. Given any two points, there is a shortest curve. And sometimes when you are in the antipodal case, there are even two shortest curves. And here curves up to a reparameterization, we identified them. So the theorem I promised is that more than Euclidean spaces, any normed vector space, even if it's infinite dimensional, is a geodesic metric space. For example, Hilbert space is a geodesic space. Here, the distance, of course, is the one that comes with the norm, which you subtract and then you take norm. And all of this makes sense in a vector space. It's a vector space, so you can subtract, and it's normed. You have the norm. And it is uniquely geodesic, which means you not only you have geodesics, you have uniqueness of them. So between any 2 points, there is a unique geodesic that connects them. And already here we see that it's not always true. There's an if and only if condition. Only if the unit ball is strictly convex, and I don't want to get into what that means. In the Euclidean case, it means that when you connect 2 points, it strictly moves into the sphere and doesn't remain on the perimeter with infinite normed spaces that can be the other case. A large class of metric spaces that I personally love, that's why I include them here, are metric trees. So these are geodesic metric spaces by definition, where every triangle is a tripod. So what is a triangle in a metric space? And that was another motivation for me to introduce this. So a triangle is you pick 3 points and you take the shortest curve between them for every pair. So this is the shortest curve between them, and this is the shortest curve between them. And now this is what we call the union of these 3 curves is what we call a triangle. And this notion allows to define hyperbolic metric spaces, for example. If you are on the sphere, you may have seen this a lot. If you are on the sphere and you produce a triangle, its sum of its angles is bigger than 100 AD. Area is a bit larger than the area of a comparable triangle in the Euclidean plane, and so on. So that's where, if you've ever wondered what does triangle mean, then that's a geodesic triangle. Now, what is a metric tree? A metric tree is a geodesic metric space where every triangle is a tripod. So when you give me 3 points, only one of these pictures can happen. That these are aligned like this. So this is the shortest curve from here between these 2 points. This is the shortest curve between them. And their union is the shortest between the first and last. That also we call a tripod, but the more fun picture is this one. So here is the shortest curve from X to Y. Here is the shortest curve from Y to Z. And the shortest curve from X to Z is already contained in the previous ones. So there isn't a new path. So this is a tripod. So a tree has branches and it goes on like that. It never has a loop, but this is what we have in mind with a metric tree. Of course, the finite trees look like this. The distance between the 2 points is the shortest path you can take to go from one to the other one. Probably this will be the one here. This can also be done with graphs where every edge is given length equal 1, or maybe we add more fun and each edge has its own scale or weight. But yeah. Okay, so more examples. The plane minus a point is already interesting. So here you are in the plane, and this point is missing in the, say it's the origin without loss in generality. Then for points that are opposite this point, there is no shortest curve connecting them, because, well, the shortest you try is going this way. Of course, we measured the length of the curves using the Euclidean distance that it has. Then you have to make some kind of loop around it and then continue. And every curve you give me, I can do better by going further inside and then making a tinier loop to avoid that point. So the infimum of the length will be equal to x minus y, but this infimum is not a minimum. It's not realized by one single curve. Okay, you can get as close as you wish to this distance, but there isn't one single curve doing that. So in this case, just missing one point ruins everything, that there is no geodesic between the 2 points. Now let's look at another extreme. With circle, we already saw that if you choose antipodal points, there are 2 geodesics connecting them. With the sphere, you have more room and more fun. If you pick this North Pole and South Pole, my picture will of course not be great. Any part of any great circle that goes between them, this one, for example, goes from the behind, will be the same length. So all of these will be geodesics. So there are infinitely many geodesics connecting the North Pole to the South Pole. If you have closer points, actually you get unique geodesics. But with the antipodal points, you get infinitely many. Okay, and now here comes a big clarification. Just like the word metric in the context of Riemannian manifolds had 2 meanings, geodesic also has 2 meanings in this context. So if you are on a manifold and you want to find the shortest curve, then you define a set of ODE by use of calculus of variations, whose solutions satisfy the so-called geodesic equation. And if a curve is going to be a shortest curve, even locally, then it has to satisfy them. So we call a curve geodesic if it satisfies this set of ODE. But the point is that it could happen that some curves satisfy these ODE. They are geodesics in that sense, but actually they are not the shortest curves globally. Maybe the simplest example of this is you have the sphere, okay? And then you start at one point. Say you start at North Pole, and you move in a geodesic curve, the shortest curve. And when you stop at any point, you can, that curve is at least one shortest curve between the 2 points. You move further, and still it is true that that curve is the shortest between its endpoints. You reach the South Pole, and it is still a shortest curve. But then when you continue, the moment you pass, then it is still a geodesic. It still satisfies the same set of ODE. So in the sense of Riemannian manifolds, it is a geodesic, but in the metric space definition, it is no longer a geodesic. It's not minimizing the distance between the length of curves between its endpoints, because one could go better by going from the other side, from behind the sphere. And this green would have been a shorter curve globally compared to this blue one. So anyone familiar with Riemannian manifolds will be familiar with these terminologies. So I wanted to add this clarification between what it means to be a geodesic in the Riemannian metric sense versus in the metric space sense, but they are very closely related. For example, locally at least, any geodesic in the Riemannian manifold sense is actually a geodesic in the metric sense. It's only the global issues that need to be taken care of. Another difference is that the study of geodesics in Riemannian manifold theory uses a lot of ODE and calculus variations, but these tools are not available in a metric setting. Remember that you don't even have a proper derivative in the metric setting. Okay, so that ends actually my examples in the Euclidean and Riemannian setting. My future examples will be in Euclidean spaces with different norms. And there we will prove stuff about particular structure of the geodesics. Until that video, thank you so much, and thanks for watching this. Please subscribe if you have not yet, and see you in future. Bye.